Practice exam for Unit 4. So this first question has us going through two different ways to add carbon. So one of the ways to add one carbon is with a nitrile. That usually involves an SN2 reaction, CN minus, or a Grignard and carbon dioxide, CO2. You have to use a Grignard here because this carbon is sp2 hybridized, so you can't do SN2s. So you have to turn this into a Grignard, so use magnesium. That turns into a Grignard. Then you add in step 1 CO2, and then the second step H plus. So I should have actually made 3 steps here, pretty better. That makes a carboxylic acid. So one of the ways we made carboxylic acids and adding one carbon was that nitrile and Grignard. How do we turn something that's not very reactive? Carboxylic acids are the bottom of Mont Carbonyl. One of the ways we do that is SOCl2, and that turns a carboxylic acid into an acid chloride, right? All the way back up the mountain. And this one, you're given the reagents and the product, and it's a carboxylic acid. So what could that came from? Like, it could have came from lots of things. It could have came from an acid chloride. It could have came from an anhydride. It could have came from an ester, right? It could be any of those things. So it didn't matter what it did, as long as you realized it needed to be one of those 3 things. Number 2, which reagent is most likely to react below amine or alcohol and why? Draw the mechanism, the product, and label all steps for the reaction below your choice of amine or alcohol. So the best choice is amine because that's more reactive because it holds its lone pairs less than oxygen. It's less electronegative. That's why. Doesn't matter which one you choose. You get the product, but amine's the right answer. First step is proton transfer, protonation. Then there's addition. Another proton transfer. Show the arrows here. I didn't. We should have the arrows on here. Make sure you're getting rid of the thing you want to get rid of, right? With an ester, you want to get rid of this piece. Proton transfer, elimination, and then deprotonation, just proton transfer gets to the product, right? So make sure you label the steps. Make sure you did those things as well. Number 3, mechanism, label each step. So, right, make sure you're doing those things that are asked for it. Label the steps. That means that proton transfer, addition, elimination stuff. Give the missing inorganic product, means no carbons. So basic conditions, the first step is going to be add, elim, get to the product, and then Na plus Cl minus, that's the inorganic product. Again, make sure you're not doing SN2s, right? For these, if you are adding, you always add into a carbonyl, break the pi bond, right? Break the pi bond, bring the electrons down, elimination. This one, again, label each step. What is the other product, right? Protonation, CH plus, it's got to react. The thing with the charge has to react first. Protonation, intramolecular addition, proton transfer, should show the arrows. Doesn't matter here. Elimination, deprotonation, and the other byproduct, of course, is water, and that's what you're looking for there. So make sure you write and label each steps, right? If I ask to label the steps, make sure you do it. So question, why did the solvent not add? Because an intramolecular reaction is faster than inter. Also look at the product. This isn't in the product. But right, so things that happen, right, intra, an alcohol within a molecule react faster than an alcohol outside the molecule. All right, 5, mechanism and product. Again, just checking in, see if you remembered what this is a carboxylic acid. So first step is deprotonation. Proton transfer is fine, PT. And then just an SN2. And an SN2 gets you there, gets you that other inorganic product. So SN2 there. All right, so for this one, number 6, mechanism and arrows. Should be able to label the steps too. How do I know if I shouldn't add or deprotonate, right? How do I know the proton transfer route versus the addition route? So if you see this, right? So if you OH minus could add here and it could add there, right? But you don't see any carbons with alcohols on them, like 2 alcohols, right? Two oxygens. So that's probably not what's happening. You look for alpha CHs. So this aldehyde doesn't have any alpha CHs, right? Remember, this does not, that's an aldehyde CH. That's not an alpha CH. So there's only one type of alpha CH. So you deprotonate that, make the enolate, right? And you could draw it with a negative charge on 3 if you wanted to. That adds in. We make a tetrahedral intermediate. You can do a proton transfer because you made water here, right? You made water here. And then that new OH minus can do an elimination to kick out the OH. Now, some people say, I know I've talked about this before, I've said this, OH is not a good leaving group, right? OH is not a good leaving group. But why might this be an exception to that case? Because look at all these pi bonds lined up. Look at all the resonance that you've created, right? By doing this elimination, you've created a whole conjugated system. So that's allowing for more resonance. That's why OH minus will let you do that elimination there.
Carbon.
Yeah, absolutely. So if you wanted to draw it, then enolate like, so it looks like this, whatever, that's totally fine. Yep. If you like to draw it like this, that's okay. Yeah. So I guess maybe one of the other, so OH minus is the catalyst, but there's also I also made water here for sure. Yep. There's water there, right?
Okay.
That's what this is making for sure. So number 7, a couple of things you can look at this. First, you need to recognize basic conditions. LDA is a really bulky base, so you're not going to do any additions. It's too big, but you will do deprotonation, so it's proton transfers. You have lots of possibilities, lots of alpha carbons, alpha CHs. Carbon 1 has alpha CHs, 3, 4, 6, and 8 all have alpha CHs. Now, but the ones on 6 are more reactive because when you make that enolate here, you can do resonance either way. So that's the more reactive nucleophile. And in this case, because it's all in one molecule, you're actually going to add in, so a nucleophile here, it adds into the carbon of the carbonyl group 2, so it makes a 1, 2, 3, 4, 5-membered ring. Right? I drew it ugly, then I drew it pretty. You do a proton transfer. Right? We do a proton transfer. H takes the O minus takes the H from nitrogen. Right? That deprotonates that. And then N minus does a proton, another elimination in E2 here, or in E2 here. So you're gonna make this, and you're gonna make OH minus. And some people ask, well, why? Again, why is OH a good leaving group? OH minus is not a, right. So let's think about the situation. What's more reactive? LDA with an N minus or OH minus, or the oxygen with a minus? Nitrogen with a minus is actually more reactive. So this is actually a more stable thing we're going down towards. And again, you're seeing that conjugation, right? That pi bond that can be do resonance there as well. Another thing to look at, right, as you're looking at these, right, I drew this squiggly line here because if you took this squiggly line and kind of took one step backwards, like did like a retrosynthesis, you could see maybe that on the side where the 2 carbonyls are at, like right here, as one side, that's going to have the negative charge, and the other side, right, carbon 2, right, is going to be here, and 6, that we can split that. You can kind of, I can look at this and say, oh, that's where that's coming from. It's a way to look at this in some ways. Label the steps, mechanism. O minus here is our catalyst. And notice how it matches the ester. So could this add in to 6? It could, but it would just get the same ester back, right? So what else it could do that's more productive, I mean, if you look at this, you can say, well, wait a second. This can deprotonate, so I need to look for alpha CHs. Well, so I'm looking for the ceto bond O's. So obviously there's no carbon there. There's a carbon on 5, but there's no H's. There's an aldehyde. That's an aldehyde CH. That's not an alpha carbon CH. So carbon 2. So you make the enolate, deprotonate. Again, you could just put the negative charge on 2 if you want. It adds in, right? Again, drawn it ugly. 1, 2, 3, 4, 5-membered ring. Make the tetrahedral intermediate. You're going to do a elimination then. Kick that out. And that gets you to the product. So basic conditions, deprotonation, proton transfer, addition, elimination, you're there. So last one here, mechanism, label each step. So this is back to, can you remember how to make an enamine? So this guy right here is an enamine, but it can be a nucleophile. It's like an enol or an enolate. The carbon is nucleophilic. So some folks like to draw the resonance structure of it. We can do that too. But let's just do this first. Proton transfer, H plus is the most reactive thing. It's going to protonate the oxygen. We're going to add. We're going to do another proton transfer, draw the arrows in. Should draw the arrows in. All right, elimination. That gets to an iminium, and then we take those alpha CHs and we can turn that into a deprotonation elimination, that enamine. Enamine's a good nucleophile, and it's nucleophilic at the carbon, so electrons come down, pi bond adds, does an SN2 addition substitution. So there you go. That's it. So I might have made it turn it back into an enamine. So the way you turn this back into an enamine is this an elimination protonation, proton transfer, so that would make N plus H plus is the final thing to make that enamine. So sometimes people like to do this too, if they feel more comfortable, like the enolates, so you can draw a resonance form of an enamine. Right? There's a way to, the resonance for an enamine would look, but maybe it's easier to understand how it reacts. It's like this. All right, so maybe that's easier to understand, that's where it's electron rich, and so that's where it adds. But it's the same. These are resonance forms of each other.